I think it's my job in this symposium to take the long-term view for you. Cosmology really does take a long-term view. We worry about timescales of thousands of millions of years, and it's extremely hard to persuade the funding agencies to take such a long-term view as well. But we try. Okay, cosmology is the study of the universe, its structure, its beginning, and its fate. I'm going to tell you in the next 35 minutes or so what we know about the Big Bang Theory and specific issues such as evolution on the grandest scale, from the genesis of matter to the birth and death of stars and of entire galaxies of stars. Now, the first concept that it's important to get across is the incredible distance scale that we deal with. Galaxies are very far away. Light from them has traveled through space for millions of years. In other words, when we study distant galaxies, we really are using space as a sort of time machine. A geologist digs deeper and deeper. The oldest rocks on the Earth are perhaps 3,000 million years old. Meteorites, the oldest rocks in the solar system, take us to maybe 4,500 million years. But the cosmologists can do far better just by looking out into space. For example, the center of our Milky Way is some 20,000 light years away from us. Light has been traveling for 20,000 years to get from there to us. The nearest large galaxy, our sister galaxy, as it were, the Andromeda galaxy, is 2 million light years away. We're seeing light from it emitted at the dawn of Homo sapiens. The most distant galaxies known are more than 10,000 million light years away. We're seeing light from them well before the solar system was created and even thought about in some sense by any stars. The light was emitted so long ago that we can begin to talk about the universe being a large place and think about the creation of the universe. The universe is not so big that we cannot try to understand its origin and its evolution. I'm going to tell you about how creation is viewed. In a sense, you can think of this as the modern scientific myth with the aid of modern telescopes. That's the Big Bang story. It replaces the gods of the ancients and even Adam and Eve. The difference with the modern myth is that science is based on hard fact. But I use the word myth because it is, after all, a theory, a hypothesis, and we try very hard to confront it with predictions and facts that we observe by looking through the largest telescopes. So let me begin by reminding you that galaxies are the building blocks that I deal with. And so on the left, you have sort of an aboriginal painting view of the Milky Way. There are teeming with life, perhaps, or whatever it means. On the right is a very modern picture taken with a satellite that looks in the infrared part of the spectrum and is able to peer through the murk of the galaxy and actually give you some feeling for the shape of the Milky Way. So the center of the galaxy is in the center of this peanut-shaped bulge, and the sun would be, if we could place ourselves there, sitting somewhere near the edge of this saucer-shaped distribution of stars. There are some 100,000 billion stars or so. The sun is one of many. Now, these galaxies are the galaxies like this. Many are found throughout the universe, and they are the tools with which we do cosmology. So, on the right, you have a cartoon which depicts the expansion of the universe. This was something that Edwin Hubble over there, first discovered around 1929. He never really convinced himself that there was such a thing as expansion. He measured the redshifts of the distant galaxies. And it was in the context of Albert Einstein, who came to visit him in 1930 and peered through the telescope to convince himself that the universe really might be expanding. This was something that Einstein himself had actually not realized until two other cosmologists in the 1920s, Alexander Friedmann and Georges Lemaitre, had found that this was a very simple explanation for what Hubble had discovered. Indeed, they invented their model of the expanding universe before the observations came along. So what is going on? Well, imagine three points, three galaxies. We're on a balloon here, expanding. notice the galaxies themselves are not particularly expanding, they're just moving apart as the balloon expands. Wherever you are, imagine any 3 points on the surface of this sphere, they would seem to move apart one from another. Well, what, of course, all this implies is an origin in time. And the man who pushed this to the ultimate conclusion that one can draw from the idea of an expanding universe was George Gamow, a Russian emigre who came to the United States in the 1930s. And what he realized was that if one took this idea the universe was expanding, there once was an early phase when it was very dense and very hot. And he pointed out that in the first few minutes, although the universe now might be many billions, many thousands of millions of years old, in the first few minutes it once reproduced the conditions inside a star. This meant that at the very beginning of the universe, for a few minutes, it was hot enough to actually produce, by thermonuclear fusion, the light elements, the same process that go on inside the sun. For example, you see here the predictions of helium and of other light elements, deuterium and lithium. All of these are made inside the Big Bang, and the remarkable thing is that when one looks at the observations, one finds a simple concordance that matches the predictions. And although we think these elements, some of them, can be made to some extent in stars, the bulk of them is certainly made it cannot be made in stars, and it's regarded as one of the great triumphs of the Big Bang theory to account for their origin. First conducted by Gamow. Now, the ideas that the Big Bang, actually, then, the expanding universe, rests on essentially three remarkable pedestals. There's the expansion of the universe, which tells us there was a dense and hot origin. There was this notion that the universe, therefore, had a very dense and hot past, during which light elements were made. Helium, remember, accounts for something like a quarter of the mass of stars, like the sun, although it's rare on the Earth. Finally, the fact that the universe had this dense, hot phase led to another remarkable prediction, the third pedestal on this table here, and this was that as the universe expanded, the remnant of this radiation glow should be left over today. And this led to a search around in the 1960s, and the search culminated in the discovery of a glow from all around space called the cosmic microwave radiation. It was measured at radio frequencies, and what has been found only rather recently, it's been confirmed only rather recently, is that this radiation has a distribution of wavelengths, which is shown over here. This is the wavelength of the radiation, which approximates that of a perfect black body. So it's hard to appreciate from this, but the error bars, the uncertainties, follow exactly, in the measurements, exactly the predictions of a black body, which is an ideal spectrum that one would find inside an ideal furnace. Implying that all of the radiation, this very dim relic, it corresponds today to an extremely cold black body because it emits mostly in the radio of only a few degrees above absolute zero. This was something that was actually predicted to be more or less at that temperature by the students of George Gamow. This radiation then must have been produced in a very hot, dense furnace. Essentially, only the early universe, the beginning of the universe, could have provided this environment to give us this glow from all over the sky. There's an interesting quote here from the cosmologist, the great Russian cosmologist, Yakov Zeldovich. The point of view of a sinner is that the church promises him hell in the future, but cosmology proves there was a fiery hell in the past. It's hard to conceive of the immense temperatures that occur at the very beginning of the universe, but they have led to big developments in our understanding the beginning of the universe. Before I get into that, let me tell you about one more cosmologist who sort of set the theme for a lot of modern work, and this is another immigrant to the United States, Fritz Zwicky. Now, he was renowned for his eccentricity, as you can tell by this picture here, but he pioneered the way to cataloguing galaxies. And one of the relics that he left behind was the distribution of galaxies all over the sky, and the modern studies of this have measured the redshifts of the galaxies, which, according to Hubble's law, which relates redshift to distance, give you a measure of how far away they are. This means that you can reconstruct a three-dimensional map of the universe. And so over here, for example, we have such a map. Now, if we, the Milky Way, our galaxy, our Earth, our Sun, is situated right in the center of this diagram. And here, when we cannot see very easily through the Milky Way, this is the so-called Milky Way around us. But when we look up at the north pole of our galaxy, or the south galactic pole, we can clearly see many thousands of galaxies. And here, their separation from us is plotted in this direction. And you can see there are large concentrations called galaxy clusters and large gaps looking almost like voids. On the average, though, things are very roughly approximately uniform, but with great structures here and there. Nothing special about any particular direction, but galaxies all over the place. There are, again, some thousands of millions of galaxies out there in the sky. Well, this is recent surveys have been counting millions of galaxies. I'll show you an example later. And they're distributed everywhere that we can see. Our Milky Way is just one of many. Now, the question that comes to mind is, how did all of this arise? How did everything get into place? And this is where the notion that the universe had an incredibly early hot and dense phase comes to bear. The idea is the following, that if one takes Gamow's view to its extreme point, you'd not only stop when the universe was once as hot as the inside of a star, but why not go back much further in time? After all, the laws of physics say there's nothing special about that particular time. If it's expanding now, once it was even denser and hotter in the very distant past. And in the first early fractions of a second, the universe could undergo a rather bizarre transition, okay, which I will illustrate. Now, this transition, if it were not for the Big Bang, would have left a universe looking rather like this. This is more or less drawn to scale. But something happened to change the size of the universe. And before I tell you a little more about what happened, let me explain one of the marvelous things of the so-called theory of inflation. We have inflation in cosmology, just as one has it in the economy as well. Imagine a highly wrinkled balloon being blown up. All of those wrinkles and blemishes disappear, okay? And the marvelous thing about this theory is one can start off with a very imperfect sort of universe, and one ends up with a universe that is as reasonably smooth and isotropic, more or less as one sees it today. Okay, so this then is, let me now tell you the story of how this works. So first of all, on the left, I have a depiction of the universe as we understood it before 1980. There was a major breakthrough in our understanding around 1980. And in the early days of cosmology, we did have a slight problem. If one took the universe back in time, this is the universe today, you extrapolate with all the galaxies around us, and we're at some random point in here, you extrapolate back in time, then it would have expanded from some very tiny size very early, more or less the scale on the cartoon I showed you. And the problem with that is there simply has not been time enough for light to have crossed the universe from one end to the other. It's extremely hard to understand why the universe is as large as it is today, okay, and as smooth as it is today. Unless you assert the universe was born in a very special way, it's very hard to understand. And we don't like making special assumptions in cosmology. It's much nicer if one has a physical theory to try to explain these things. Well, around 1980, people from a different domain, particle physics, started working in cosmology. They had realized that the very beginning of the universe was a very hot place where one could recreate at relatively low cost, but basically on the back of an envelope, the conditions that one would need to build an enormous particle smashing machine, such as the machines like the superconducting supercollider, conditions such as they would have produced, and even larger machines. These would come essentially for free in an experiment that one had no control over, but which could have existed in the distant past at the beginning of the universe. Well, it turns out that given this notion, one could start off not from a very tiny size indeed, okay, at a very tiny time, early time, a tiny fraction of a second after the beginning, and then the universe went through a transition in phase in the same way as ice melting, actually, when latent heat, a certain amount of heat is released. In this case, it's to do with the types of particles that were in the universe, but in the same sense, heat is released, and this heat results in a dramatic expansion. Now, this expansion in scale doesn't mean anything is moving faster than light. I want you, if you imagine, it's a creation of energy in a sense. Imagine a bookshelf on which you stack your copies of Nature, and let's suppose that the numbers of Nature every week are doubled, okay? This I'm sure isn't happening yet. But you can imagine after 10 years or so, the ends of your bookshelf will be moving away at greater than the speed of light, one from one end to the other. There's nothing really moving at this great speed. One has exponential inflation. Well, something like this we think must have happened according to these theories of particle physics applied to the early universe. And you'll notice the consequence of this amazing thing. There's nothing else special about the size of the universe that we can see, the yellow dot. The universe is very, very large, and we can understand how large the universe is, why it's so smooth over the region we can see. There's nothing special about this region as there would have had to be in this case. So the other consequence of all of this is the following, that we now have this universe which inflates, and it went through these remarkably high energies in the beginning. And it turns out that the early universe then was a great laboratory for understanding, for playing with particle physics, really. Every particle that you could imagine that could have existed, should have existed, given the conditions of the early universe, when it had energy enough to recreate these particles. Sort of energies you can hope to produce by smashing them together in giant machines. As I said, that they were present in the very first fraction of a second of the universe. Now, one does extrapolate to the very beginning here. You notice that I'm talking about times, which are a very tiny fraction of a second. This actually is as far as you can push back cosmology, because at a certain point you run into sort of, it's a bit like a wall. You require a theory which brings in the quantum theory and gravity together. Up here we have sort of more or less the classical theory of gravity, which we think we understand. At the very beginning we're still waiting for the final theory. Okay, we don't have that yet, but everything else we're fairly confident about. And for example, the sort of things that happen is there was a phase very early when the forces were unified. This phase transition, analogous really to the melting of ice, happened and led to the inflation. And from then on, there were all these various particles being produced at the very high energies. Even the protons and the neutrons, electrons out of which we're made were produced as the universe cooled down from the incredibly high temperatures early on. Okay, now there came a time at which, as the universe cooled down, it was, of course, full of radiation, and at some time the universe stopped being this very hot ball of plasma and became more or less an ordinary colder gas. And from that time on, whatever radiation there was, essentially just expanded freely with the universe and has traveled freely to us. When we look around the sky in principle, we can try to look back and look for evidence from any glimmer of radiation that might have been present in the Big Bang. At the same time, structure is developing in the universe. Now, just as when ice melts, it does not melt in a uniform way, it breaks up into icebergs and so forth. In the same way, this phase transition not only smoothed out the universe, but led to structures forming. And so what I want to now describe for you is how these structures have led us to understand how the universe developed into its complex mixture of galaxies of all types and descriptions. And this shows you in sort of a cartoon way what happened. There were fluctuations which developed, and just under the influence of gravity, there were slight excesses in density around, all the way from very early, and where there was a little more matter than the average, that pulled in more matter just by the force of gravity. It's sort of a capitalistic theory in a sense. You know, the rich get richer, the poor get poorer, and so the regions with excess matter develop more relative to the regions without the matter. One ends up with structures and with regions with no stuff in between them. Okay, so that is a sketch of what we think has happened, and sort of a grand summary of all of this is the following. So we have this inflation theory where the universe went through this phase transition. It led to fluctuations in density being produced very early, and then the physics that we think we understand of how the universe expanded and interacted, the matter and the radiation that was left over, the fireball from the beginning gradually cooled down, led to, by the simple process of gravity, led to the formation of structures. Now, one of the intriguing things that I'm going to tell you about is how we can there are two ways of tackling this problem of understanding where we came from. One is to look at the structures themselves. In a sense, you look at the galaxies around us, they're a bit like fossils. They have within them, because galaxies are fairly slowly evolving things, they have within them the seeds of the information of the past, and in their distribution and in their structure. At the same time, when you look at the radiation in the sky, the leftover radiation, you can actually look back to when the fluctuations still started forming, because it was only then because back till then the universe was completely transparent. Over here you see a map of 1 million galaxies. Okay, now this is just positions. This was made a map The data for this was gathered in the 1950s, before really the age of modern computers and digital scanning, and the two astronomers that did this took 10 years to count the galaxies. Now we have ways of speeding all this up. But in any case, their data is the following. The Milky Way goes around here. Okay, so we're looking at the northern part of the sky, out of the Milky Way, and every point here corresponds to a galaxy, and some of them are crowded together, so essentially you have great clusters of galaxies looking rather like dots on this picture. And you'll notice that and there are something like 1 million points plotted all together, and you'll notice there are great clusters and superclusters and regions without stuff in, but there's no obvious place you can point to and say, aha, the universe began over there, over there. It's more or less the same everywhere you look, in structure everywhere, holes everywhere. Remarkable. It's really rather remarkable to try to understand how could all this come from fluctuations. Well, the nice thing about gravity is that it's one of the subjects that we think we can understand. We can put all of this onto a computer, and we can study this by letting the particles, which interact by the force of gravity, just laws given to us by Newton, we can now, instead of just worrying about 2 particles or 3 particles, we can put millions of particles down and use a modern computer to follow what happens to them. And so what I'm going to show you next is the way one can study how structure evolves in the universe. First of all, let me just say that we don't really know how things began. And this is sort of a sketch of 2 types of fluctuations that there might have been in the beginning of the universe, actually taken from the cover of Nature some years ago. And on the left, we have, imagine ripples in the fabric of the matter. Here are large ripples, here are many, many small ripples. One can think of this as a situation in which the fluctuations laid down by one's theory of the beginning had very large scales built in, so the biggest things formed first, smaller things formed later. This would lead to what has been called a top-down, from big to small, formation of structure. On the other hand, on the right, you have a picture in which the initial fluctuations, I'm assuming that we don't know the details for the moment, are laid down in a much more random way, all sizes, everything being more or less equal. It turns out that the theory of inflation predicts this and not this, to a first approximation at least. And what this means is that because one has small things as well as big things, here one would have a bottom-up view of formation, the small things forming first and the bigger things gradually forming later. Okay, so this is an example of sort of the things that we're rather uncertain about. How do you test any of this? Well, again, what you do is you put a lot of this on a computer. Okay, and so over here I show you 2 examples. You start off when the universe was maybe a fraction of its present size, 1/10 of its present size, and this is a cube of the universe, some hundreds of millions of light years on the side. Okay, and the particles, you can think of them as parts of galaxies. Some million or so of them are laid down in different ways. And so in this situation, it's very hard to tell, but the fluctuations are in the sense that one has this limit where one has the larger ones predominating. And in this case, one has all sizes of fluctuations. Then one follows the fluctuations on the computer. You let the regions where there are slightly excesses of density, if you imagine pointing from one region to another, over here there might be slightly more than the average, over here slightly less. In a region where there are slightly more than the average, gravity wins in the end and tends to pull more stuff in. And so the regions with more grow more, the regions with less grow less. And you end up, after a while, the universe expands for a while today with structure. You'll notice the structure is very different. In this case, one has a structure in which one has enormous concentrations of galaxies with little in between, whereas over here, it's much more random. There's structure on very small scales as well as the bigger ones. You can look at the universe, you can look at these surveys, which are being taken and being developed now, and one needs bigger and better telescopes to do better surveys. You can look at the universe and try to decide which is closer to the truth. Okay? And it turns out that the present-day universe is really much closer to this picture than to this picture. Okay? It really does not look as if it's dominated by these giant structures. There's sort of a mixture of all things that you could more or less tell by glimpsing the earlier picture I showed you. So that's the overall global view. Now here is something else that you can do. You can also ask, let's now try to zero in on a galaxy like our own galaxy. Okay? So you'll notice that many of these points are sort of merging together. Structures are making galaxies. You can't see the details from this. You can only see the larger clusters. But one has many millions. One ends up with some thousands in this picture. So it's inevitable that structures merge together, especially in pictures like this. Here's an example of what one can do on a modern computer. Okay? We're now merging together two galaxies, a big one and a small one. Okay? So one follows them some millions, some 10 million years later, it's coming closer. The effect of gravity of this on this one is pulling out the nearer bits, and the thing is rotating as well, and so it's spinning it out into a spiral pattern. One makes rather beautiful spiral patterns, but along the way one ends up at some period of this with rather messy looking galaxies as the merge is occurring, but eventually things settle down, and if one to follow this a little bit further, it would make a nice round looking galaxy. Okay? So this is the sort of way we think that one can reproduce the galaxies. Now, how do we understand this? Well, what you do when you study the galaxies, many of them are these very beautiful regular things, but what you try to do is you try to catch galaxies that are in the act of merging together, things like this, because this is how you can learn about the structure of the universe. So here's, sorry, let me just, this is just a close-up of the merger actually, and you see two things coming together at the beginning, and this is an intermediate stage, and so these are, this is on the way to merging to make a nice round galaxy called an elliptical. This would be an example of a merging galaxy. So we want to look at the universe to see if there are such things, if these theoretical notions of how structure develops in a bottom-up sequence are correct. Okay, and so here you see now two examples of what one can call shipwreck types of galaxies, merging in process. Okay, these are rather rare objects, but as you know, you often want to look for the deviance in society to understand how things really work. This is an example of it. You can notice these, look carefully, you see these tidal plumes just drawn out by the gravity as they were approaching together. Eventually this will turn into a nice round galaxy. We're catching it in the process of doing so. Here's another example of a galaxy that was apparently rather odd already from a ground-based picture. You look at it with the space telescope and you find this complex structure in the middle, indicating that this is a violent merger is going on. And now you may wonder, these are really the oddballs, are all galaxies like this? Well, here is an example of a very normal looking elliptical galaxy. Okay, it's a negative photograph, and what you do is you take a very deep exposure. Now this is exactly the same galaxy. Notice, for example, these two stars repeat over here. We're just looking at a deeper exposure. And what you can see over here are ripples in the outer part of the galaxy. It's a bit like throwing a stone into a pond. Okay, you see splashes long after the stone has sunk to the bottom of the pond, and the ripples in the gravity field in the star distributions take a long time to decay away. But even this very normal-looking galaxy had a past that indicates it most likely was formed by a merger. And here's yet another result. This is our neighboring galaxy, the Andromeda galaxy, taken just a fuzzy patch of light with the naked eye, but you can. It has this beautiful structure through a telescope. Here's an attempt to simulate it with a modern computer. And you can see one doesn't quite, one can't have 100,000 million particles. One has to make do with only a million or so, but you're getting close to the general structure of what you see there. So this is how we think we understand how things are forming. Now there is a moral in this, of course. One has to be a little bit careful. This is one of the earliest computer messages that we have. And this is the man that did it, L'homme primitif, and one has to be a little bit careful about believing everything that computers do, of course. Okay, so there's one other ingredient in all of this, which I haven't mentioned, and that is a very puzzling ingredient, and that we have to face squarely in studying the evolution of matter. Here is one of the more beautiful galaxies around. We're looking at it from the edge, the Sombrero galaxy. This is just simply would be the equivalent of the Milky Way. Now, one can measure the star velocities by taking the spectrum, and you can measure essentially that the galaxy is rotating. And you find, and this sketches a galaxy like this, the rotation speed of the galaxy. Now, the amusing thing about this galaxy and many, many others is the rotation speed as you go very, very far away from where the light is. This is the light. The rotation speed does not decline. Now, you would expect, for example, as you move away from the sun, the planets are being held in orbit by the gravity force of the sun, the rotation speed gets less because the gravity force is getting weaker. What is happening here is the speeds are not getting slower. They're staying in way out here, meaning there is lots of stuff out here that we cannot see on a photographic plate, dark matter. It turns out that 90% of the mass of a galaxy like this consists of dark matter. So that is the big problem. There are many ways to study the dark matter. These are two of the modern ways. Here is a cluster of galaxies. The dark matter in this cluster acts like a gravitational lens and distorts images of background galaxies. Here you have some of these images distorted by the dark matter in this foreground galaxy cluster. And there's another example of a galaxy. The dark matter in the halo of this galaxy is focusing and splitting up the light from a single background object. And actually, because lenses are not quite perfect, they actually make 4 different images of the same thing. A gravitational lens in action. And if you want yet more evidence for the dark matter, this is a cluster of galaxies full of gas that is seen to emit X-rays. Astronomers need to send satellites up into space to study X-rays from galaxy clusters. This is one of the more exciting results. This whole galaxy group actually is full of hot gas, and it's being held out there because there's dark matter all over the place, far more than you see in the galaxies themselves. So what we want to know from this is what the future of the universe will be. And what I've sketched over here is what one predicts for the universe, the average size as it expands, getting larger and larger with time, or perhaps it will start to collapse again, here's where we are today, into the future to give us a future crunch. Will it expand forever, getting colder and colder, or is it designed to heat up again eventually in the future? We don't know the answer. It depends on how much dark matter there is in the universe. And if we just take the dark matter that we see in the galaxies, in the galaxy clusters, in fact, that would tell us the universe will keep on expanding forever and ever. However, if we hypothesize that there is even more dark matter, stuff that is so hard to measure, so uniformly spread out that it isn't even showing up in our present measurements, then we might be in a picture in which the future of the universe, now this is on the very long time scale, some several tens of thousands of million years in the future, will eventually stop expanding and then start to contract again in the future. So how do we determine the future of the universe? Okay, it's a difficult thing. Since we can't really do it with dark matter, we have to go back to taking pictures of the universe and comparing it with our computer simulations. Here's an example of a computer simulation of 2 universes, one of which will expand forever, one of which will not. And the message is that although they do look slightly different, it's very, very hard by looking at the nearby universe today. This is supposed to be, again, a projection of a large cube of the universe, and we're looking at the galaxy distribution to show the difference. The sort of thing that you can do, though, is go to a telescope and expose for a very, very long time and take the deepest, faintest picture you can of the distant galaxies. And here is one of the deepest pictures yet taken from the ground, first exposed for some 10 hours on one of the larger telescopes, and it is found to be teeming with very, very faint galaxies, presumably the furthest ones one can ever hope to see. So it turns out that, in a sense, the universe is almost a bit like coated with these very, very faint galaxies, many thousands of millions of them, as judged by looking in this small patch of the sky chosen at random. This then is one of the ways to studying what things go on, is one of the keys to, as far away as one can, is how one can help to decipher the properties of the universe. And so over here you have another sketch of how the universe would have evolved from an explosion. Here then is the radiation that I talked about that we see now, one of the predictions of the Big Bang. Okay, now one of the major discoveries long anticipated in cosmology was that the radiation should have traces in it of the fluctuations left over from the very beginning. Just as there were fluctuations that gave rise to, in the matter, that gave rise to the galaxies we see, since the matter and the radiation were present early on together in the universe, the radiation comes directly to us. We can see back to when the universe is transparent now, but the early universe you can think of as being shrouded by a dense fog of radiation. Because the matter was so dense, we can't see back any further. And we can see back to when the universe was perhaps a few 100,000 years old from the beginning. And that was long before any structure had formed. However, if what I've told you about fluctuations, tiny fluctuations giving rise to structure is true, one should see them in the radiation. So the discovery of a couple of years ago by the COBE satellite, the Cosmic Background Explorer launched by NASA, was that here is the Milky Way, and when they look very, very carefully around the sky away from the Milky Way, some evidence for tiny fluctuations was seen. Now, this was the story before they launched the satellite. This is the Milky Way in this rather funny projection over here. And you'll notice that when they look very, very carefully at the background, it was very slightly warmer in one direction. The blue indicates slightly warmer and slightly cooler in another, only by about 1 part in 1,000. This is actually due to our motion, the motion of the Earth around the Sun around the Milky Way, through this sea of radiation. In the direction to which you're going, you see a very slight warming. Behind you, there's a very slight cooling, just by the so-called Doppler effect. However, if you now take subtract all of this out and look, now you greatly magnify what is left behind by about 100 actually. This is what the satellite discovered. There were fluctuations on rather large scales. These correspond to tens of degrees all over the sky. And these are deviations. The radiation is actually almost the same to within 1 part in 100,000, 99.999%, but the deviations are, we believe, the source of the structure. Now it so happens that these deviations that one saw with this particular satellite are actually equivalent to looking at the universe in very different directions, a few degrees apart on the sky and even further. And these actually are looking at different parts of the universe that in fact take us back to the very, very beginning. I mean, one can only imagine these fluctuations were laid down soon after the beginning. If one asks what actually were the precursor fluctuations from which the structures around us formed, they would be rather smaller. They would not be resolved on this map. One actually would need a new experiment to look for them. So this then is the future of how we hope to go in cosmology, to do experiments, and I will show you predictions for such experiments. So here, for example, you have what one could do with a new satellite proposed in the future. There's a European project with UK participation, which is being considered by ESA to do just this, to look with finer resolution at the sky, at the microwave background. And here are 3 different possibilities for the amount of dark matter in the universe, really, which lead you to slightly different predictions of how the universe evolved. And you can, and if you look at these with very subtly, you can see slight differences. And it's only by mapping the universe out with exquisite detail that one can hope to one would hope to see fluctuations from the beginning. So these are predictions of what you might expect to see with a bigger and better, and obviously, unfortunately, more expensive satellite. At the same time, we have a telescope up in space, the Hubble Space Telescope, which is taking snapshots with about 10 times the resolution that one can do from the ground. And so some of those galaxies, which are just fuzzy points of light that I showed you, are now seeming to be like this. Okay, this is recent data from the Hubble Space Telescope after they improved it with what essentially amounted to contact lenses. They corrected it. And now you can see that some of these distant galaxies, a rather high fraction, look like these galactic shipwrecks, galaxies in collision, galaxies in merger. These are galaxies now very, very far away, more or less at the observable end of the universe, as far as we can see, looking way back in time. So things are sort of falling into place, we think. There is evidence as one looks very far away that we may be seeing the evolution of the giant structures. All of this, as I said, is on a very, very long timescale. We're looking back thousands of millions of years, and it's all going to take bigger and better telescopes. Unfortunately, many of them have to be in space to do better, to really take us back to probing not the beginning and how we evolved from the beginning. But I think inevitably it's going to come. Whether it will come in 2 years' time or 10 years' time, I don't know. But I'm confident that we will learn far more about the evolution of the universe, which is really beginning to probe the surface in cosmology now. Thank you.
Could I ask you a question, Joe? You know, in the past 2 weeks, we've published 2 papers, 2 measurements of the Hubble constant. And these give a value for the age of the universe of about, should we say, 10 billion years, which is less than the age of some stars in our own galaxy. How does one square that?
You have to be extremely cautious about approaching measurements of the Hubble constant. The reason is the following. That
even when they're published in Nature?
Even when, I'm afraid so. The reason is that in each case, they were looking at just one particular galaxy, in a distant one, admittedly, to try to measure its distance. Unfortunately, the galaxies that they were choosing are themselves in a giant cluster, which we are on the outskirts of. And therefore, we are not full participants, those galaxies and us, in the uniform expansion of the universe. So there are very uncertain corrections to be made, and astronomers are still disputing the degree of those corrections. And so you will find that there are some astronomers who maintain very strongly that the age of the universe from the Hubble constant could be probably twice as large still, and not violate any data. And finally, I would say that even if this turns out to be right, that the expansion age does settle down to be, let us say, 10 billion, 10,000 million years, does that contradict anything that we know? Well, it is true that our current models of the older stars give somewhat larger ages, but those are models, and there are enormous uncertainties that goes into those models. My bottom line would have to be the age of the solar system. Okay, we're safe. That's only 4.5 billion years.
One more question, if there is one. Here we are.
Yes, you brought up the issue of the dark matter, that this may actually be an order of magnitude greater than the visible matter. What is it made from? Or what form is it?
Okay, we don't know. There are two distinct schools of thought. One of them maintains that it's made from elementary particles, very weakly interacting ones, that were produced in the early fireball, the early heat of the universe. Most of such particles that could exist would have existed. Most of them would have decayed away, but it is thought from our understanding of the symmetry of the forces that the lightest one of those particles would have survived if it existed. Okay, so that's one candidate for the dark matter, a particle very weakly interacting that could be out there if such a thing exists. Another candidate is very, very different, and this would simply be very dim stars. And again, the numbers of such things are very uncertain, but there we have the advantage that we know that such things exist, and but we don't know how many there are. So one has two different possibilities, and only more future observations will distinguish them.
Many thanks indeed.
Oh,